The properties of substances like water, a molecule, or salt like a crystallinus of sodium chloride depend on the nature of the intermolecular forces holding the particles together. And we talked about those, the strength of those determine properties such as melting point and boiling point. But now we're going to study the property of solubility. And what we have to now add is a two-component system. We have the solute and the solvent. So what we have to do if we're going to dissolve something like sodium chloride is that we've got to disrupt all these ion-ion interactions. We also have to disrupt a lot of the water-water-hydrogen bonds. So we have to disrupt interactions in both the solute and the solvent and replace those with something acceptably and reasonably strong. In this case, we know sodium chloride dissolves in water. So we have individual sodium ions surrounded by the dipole water and individual chloride ions likewise surrounded by water. In any strong relationship, you have to have give and take on both parts. So in this case, we're breaking strong interactions in the salt, strong interactions in water, hydrogen bonds, but we replace those with reasonably strong, acceptably strong ion dipole interactions. So the sample dissolves. But if we look at another kind of salt, for instance, calcium carbonate, which consists of calcium 2 plus and carbonate 2 minus, these interactions within the solute are so strong that if we were to add water, water cannot simply tear those interactions apart and form individual calcium surrounded by the water and carbonate surrounded by the water. So these are so strong that the replacements aren't effectively strong enough, the ion dipole interactions, if it were soluble, to replace these really strong interactions, so it doesn't occur. So calcium carbonate is not soluble. But if we had something like sodium carbonate, sodium sulfate, sodium phosphate, these are all soluble, actually. They're all soluble in water because the charges between the ions are just 1 plus and 2 minus, 1 plus 2 minus, or 1 plus 3 minus. They're not 2 plus, 2 minus. Now let's consider another kind of solute, octane. We all know octane is a liquid gasoline at room temperature. So there must be intermolecular forces between them. They're LDFs. They're weak, but it still allows it to be a liquid. Now, is this going to be soluble in water? And again, so these aren't very strong. The interactions among water molecules themselves are strong. So what's going to happen? If this is to be soluble in water, we're going to have to break up the strong water interactions and replace them with, if you think about it, induced dipole interactions, the dipole being water, and it will induce dipoles in this molecule octane. So here's an example. A few molecules of octane might be soluble in water, limited solubility, but if I add more and more and more, we have to disrupt so many hydrogen bonds which are strong and replace them with these weaker interactions that what happens is we get just a phase separation. These molecules would rather stay put. Not that they interact so strongly, but they'd have to disrupt too many hydrogen bond interactions with water. So we actually get octane formed on top in two different phases. You know, if you have enough gasoline, it's not soluble in water. So this is an example in which, in this particular relationship, the strong partner hydrogen bonds are not willing to break up their strong interactions to produce abundant weak interactions of dipole, induced dipole with the octane. Now here's another example of a fatty acid. Notice this long hydrocarbon tail, but with a polar end. So this is an example of an amphiphiles. Now fatty acids are going to interact weakly through LDFs and some polar interactions here, possibly hydrogen bonding. But now, will these two basically come together? Can I add these to water and will it dissolve? Well, again, we have to be willing to break up a lot of hydrogen bonding interactions, and it turns out a little bit of this single chain amphiphiles is soluble. But if you get too much of it in solution, it still is breaking up too many interactions with the water. And of course, these non-polar chains don't like to be in water because those interactions aren't very strong. But what happens is these self-associate to form a micelle, in which the non-polar parts are buried inside, just interacting through LDFs, and effectively the polar head groups here, the carboxyl groups, are basically surrounded by water. So in a way, as it is very slightly soluble, if we get enough of these in solutions, we get a phase separation, just like we saw with the octane, because there's too many weak interactions that would be formed, and you'd have to break up too many hydrogen bond interactions for it to be completely soluble. Hence, we get a phase separation and micelle formation. The same thing can be considered phospholipids, which are double chain amphiphiles. Here we have two nonpolar chains and a polar head group. And again, these form a little bit stronger interactions because there'll be LDFs between the nonpolar parts and basically H bonds, polar dipole interactions with the head groups. But again, if we're going to ask these to dissolve in water, we have to be willing to break up a lot of the water H bond interactions. So you throw it into water, a little bit of it might be soluble, but the fact is it's not very soluble, and if enough were to be generated in solution, it would want to self-assemble and form a bilayer. And this is a view of a bilayer. And again, here on the outside, this is another view of a bilayer. Water would be on the outside, water would be on the inside. Again, this is like a phase separation, if you think about it, in which the nonpolar groups are not at all exposed to water. They're just exposed to themselves. And in this case, we have an aqueous compartment on the inside and, of course, water on the outside. So again, water is not willing to give up its strong hydrogen bonding network just to facilitate the complete dissolution of a phospholipid molecule. But it is willing to produce a structure like this because the nonpolars don't have to interact with the water. We can extend this interaction to carbohydrates. Here's an example of cellulose, a polymer, homopolymer glucose, 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 and all these reds are oxygens. Well, if you look on an edgewise, these can all form hydrogen bond with another strand of this polymer of glucose. This is the molecule cellulose, and another one and form these very, very closely packed fibrils. Now the question is cellulose soluble in water? And we know it's not, otherwise trees would dissolve. So again, we must not be willing to give these up, or there must be too strong of interactions here to be replaced by the water. And it turns out because those are so tightly packed, they're not very accessible. Water can't get in very easily. So in fact, this molecule, even though it's filled with a lot of polar OHs and has internal OH hydrogen bonds, will not disrupt a water hydrogen bonded network because the water simply can't penetrate in here. So in this case, cellulose is homopolymer glucose is inside. But if we take a branch polymer of glucose, and the branching makes it less compact, less internal hydrogen bondings between those linear strands that we saw in cellulose, well, in fact, this is more accessible to water. So water can form hydrogen bonds with this very readily. It's a very polar molecule. So water is ready to give up this hydrogen bonding network because it can form a lot of hydrogen bonds here, and they're accessible to each other. And the internal hydrogen bonds in this branch glucose polymer basically are more open to and accessible to water. So in fact, this amylopectin is actually much more soluble than cellulose. Not hugely soluble, but more. And again, it's less packed, more water soluble, more water accessible, more water soluble than something like cellulose. Finally, let's look at a protein. Here's the three-dimensional structure, cartoon picture of a protein. It's got a very polar backbone. It's got nonpolar, polar side chains pointing all over the place. Is this soluble in water? Are proteins soluble in water? Well, again, we have this hydrogen bonded network of water. Is water willing to break this up? Can we actually form hydrogen bonding interactions with this? So what happens? It turns out this protein is soluble. Most proteins are. And you can see here in this picture, the red dots represent water molecules interacting all over the surface here. There's internal hydrogen bonds within the protein. There's internal London dispersion forces. There's internal ion-ion and dipole-dipole interactions. Which stabilize the folded protein, but also there's these interactions with water on the outside. So again, we don't have to worry so much about breaking up the hydrogen bonding network in water, or breaking up too much of the interactions that stabilize the three-dimensional structure, because in fact, it can still be stabilized in water. So proteins are soluble in water, and they don't lose their structure when they are soluble. Now let's consider one final example. We're going to add another component to this now, and that's the ligand binding to a macromolecule. So again, we have a protein, soluble protein that would be surrounded by water. And it's going to interact. This particular protein binds sulfate, and we know sulfate has a -2 charge, very charged. It's going to react very well with hydrogen bond with water through dipole ion interactions, and you could put a lot of these in solution if I add sodium sulfate, which is soluble. So I throw these in. Now the question is, can this sulfate bind to a little pocket in this particular protein as illustrated down here? Well, it's sort of the same thing. Is this sulfate willing to give up this ion dipole interaction? Is this little pocket in the protein willing to give up any water interactions that might be there, because the pocket's probably accessible to this? Well, in fact, it is. And what happens is when the sulfate binds, we basically was able to give up these ion-dipole interactions and reform the hydrogen bonds. We lose some waters that were in this binding pocket, but they can hydrogen bond with themselves. Now the sulfate sitting in the binding pocket turns out to be really stable because there's a plus charge in the binding pocket, and other side chains and backbone of the protein that can interact through dipole-dipole interactions and hydrogen bonds. So this is a three-component system. We're dealing with the water, the protein, and the sulfate. And it turns out we can give up some of these interactions to form this especially tight interactions, especially because there's a plus-minus interaction between the -2 sulfate and a plus charge in the protein. So in summary, when you're thinking about solubility, you have to think about both the solute and the solvent. And if one of those is willing to give up some really strong interactions to engage with the other, of course they have to be replaced with some reasonably strong interactions, then the substance, the solute, will be soluble in the solvent. If not, if the interactions are too tight either in the solute, such as 2 plus ions, 2 minus ions, or in the solvent, like strong hydrogen bonds within the water, to break those to form weaker interactions, one solubility will not occur.